Welcome to a lesson with Dr. Powell. Let's take a look at how we could take the derivative of a function whose expression is defined by two pieces, such as x to the cosine x, or x times natural log x. Notice we can box the different pieces of the expression, exponentiation, multiplication, and there's a myriad of other types of things that have two pieces that we can work with. Now, we're going to label these boxes as A and B, and let's concentrate on this particular function right here for now. Okay, so remember that a derivative represents a rule for how to move from run to rise on a tangent line of the function. So in particular, in our case, for a run of x, we have a rise of the function, which we could label as dy, but I'll label it as dg. But it means the same thing. The rise of the function g, or well, not the function g, the tangent line to the function g at a particular point. And we can kind of represent or draw a line to represent the tangent line. And think of this point as being some point on the curve g. Okay, so as dx changes, a will be changing and b will be changing. Both of these boxes will be changing because they both depend on x. They're both functions of x. So in some sense, we could kind of think of a pair of changes, a change of dA and a change of dB happen alongside with the change of x. They kind of happen together at the same time. Well, if we're going to be thinking formulaically of a nice way of actually taking a derivative, we might need to change our viewpoint a little bit from this, because it's kind of hard to think about things happening at the same time. So we're going to look at something that actually doesn't happen, but get back to what really does happen. So let's go for that. I'm going to think of the change of x that I've just drawn, but I'm kind of think of it as happening in a sheet, flat sheet or a plane or something like that. And I'm going to think of the y-axis or y values as being vertical. Okay, so going up and down. Now, if I think about the rise of the function g, I'm up here. And this is the tangent line. So I'm kind of thinking of the xy plane as kind of occurring like this. I've kind of turned it so I can get a good viewpoint of it three-dimensionally. All right. Now, why did I do that? That's because we're going to consider something that doesn't actually happen. We're going to move, thinking of the function g as being x times natural log x, this being a and this being b. When dx changes, that's like a and b have both changed together. But what if only one of these boxes changed and the other one didn't? So we can think of, in particular, we can think of for the exact same dx, but going in a different direction. So thinking of a similar plane, but let's just go off in another direction because it's not really what happens. So let's think, if x changes, the same basic dx, but in a different direction, and I'm going to put a little a right here to signify that we're going to be thinking of the a box changing, but the b left constant. Now notice if the b box was left constant and just given the value at this particular point, we get a new function where this is the only thing that's variable and this is just the constant that it is right at the beginning right here. We do, and it has a slope and a tangent line. So as dx goes this way, then what happens? we're going to have a rise in the over a function. Maybe I'll call that function, the new function, where this thing is left constant from that point, call it GA maybe. So it'll have a rise going in that direction. Okay, and maybe I'll erase this right here. Okay, so we can think about this for a minute. So it goes in that direction right there. And let's label that as DGA. Okay. All right. Now, and remember that we were going in that direction right here, and that's what dx was in the regular plane. Now, let's think about, okay, so we do that and we got to this point when g has been affected. Now let's start from this point right here. And let's think of a as being constant now and only b changing with the same, along the same dx. What should happen? Well, if we think about it, when we go in a different direction, we should land our inputs. So maybe our input should be right here, and we'll draw the line parallel right here, the run. So if dx changes where, but let's draw a plane actually now going in this direction right here. So we have kind of three planes going on, one that way, one this way to hold a growing, and then here for b being the one that changes. So if b being changes, then we have our dx pointed in that direction. But the two should match because dxa and dxb, meaning the change of x if for the function where a is changing versus the one where b is changing, we should get back to the regular dx where they're both changing and they both change by the same amount. Because this has changed and that has changed, well, they both have changed with respect to x the same way. So our picture should really land and match up. Now, if it matches up, let's think about that for a minute. This is going to have a run starting from this point, and it's going to rise. And where should it land? It should land right on the original y value. That's because, I mean, this is a tangent line right here, and we're up close where we're thinking of everything as being a tangent line. And we want this to match because the overall rise that's affected by this changing, then that changing should take us back to the exact same spot. Kind of a neat feature, because what we get is we get that the rise of, let's see, so let's think of this right here, this little part right here as being dgb. And notice what we get. We get dga plus dgb is the full dg that actually happens. So this rise, the real rise, is just the sum of these other two rises, which we can actually use, all right? And it's actually tends to give us something really, really neat. So to think about ratios then, let's suppose that we're changing by the exact same run dx for this guy and that guy, just as we were thinking of in the picture. And so we can, this addition of rises really turns into this thing. dg dx is equal to dga dx. So the derivative of this part where a is the variable and b is constant with respect to x plus dgb dx right here. And maybe I'll erase this so we can kind of see that a little better. Okay, maybe do that again. Okay. If you think about dx as just being the same thing across the board, then you can just divide this equation by it, and it will be a preservation of ratios, which is what we wanted, assuming that dx is a positive run on the tangent lines. So we get that this ratio is equal to the sum of these two ratios. So we get this derivative is equal to the derivative of that scenario plus the derivative of that scenario, where this is constant. In the next video, we'll actually work through those details. Thanks for watching.